transformation of functions. So let's talk about how graphs of functions move around on the graph and what causes them to do this. So we'll first start with a theorem. Let f of x be a function and let h be a fixed real number. If we replace x with x minus h, we obtain a new function, g of x, which is equal to f of x minus h. The graph of g has the same shape as the graph of f, but shifted h units to the right if h is greater than 0, and shifted absolute value of h units to the left if h is less than 0. So what this theorem is saying is that if I add or subtract a number from x inside the function, it's going to move the graph either to the left or to the right. So let's take a look at the example 1. Sketch the graph of a function f of x equals x plus 2 raised to the third power. So to look at this graph, let's first look at the standard graph, or the parent function. So the parent function would be f of x equals x to the third. So you can see the general shape of the function there in the middle. So what we're going to do, because we're adding to the inside, we're going to move this to the left. Alright, so I'm going to add the parent function to our graph in red, and it's just an approximation so we can kind of see where we're going. So it looked kind of like this, and I'm no artist, so just forgive the way that looks. Okay, so let's talk about f of x equals x plus 2 to the third power. So in standard form, this is x minus negative 2. So because it's minus negative 2, we are shifting to the left the absolute value of, so h is less than 0. So we would shift this 2 units to the left. So everything's going to shift this way, 2 units. So this graph would, and again, I'm not an artist, so see if I can do better than that. It would look roughly like that. So you can see, and again, my graph is a little bit disproportional, but it's shifting 2 units to the left. In your homework, it's going to do the graphing for you, so you don't need to worry about drawing pictures. You just need to know and understand that it's a shift 2 units to the left. Okay, so the next function is an absolute value function. So before we begin, let's take a look at the parent function of the absolute value function. So here is the parent function of the absolute value function, f of x equals the absolute value of x. And you can see that it's a V shape. So our graph is subtracting 4. So h is greater than 0, so this would go to the right 4 units. So again, let's put the parent function on there first, and it is a V. Looks something like this. And we're going to subtract 4, so we are going to move it 4 units to the right. So that would move that there. So our function would look something like this. All right, so the caution in this section is just talking about the positive and negatives, and there's two thoughts of it. You can think about it in standard notation, which is x minus and then whatever the sign is on h, or you can just think of it as doing the opposite of what the sign is telling you. So if it's subtracting, you go to the right. If it's adding, you go to the left. That's really not appropriate, but it works. So if we add or subtract inside the function, we move left or right. Okay, so the next transformation is vertical shifting, and this is actually the last transformation that we do on the homework, but it's appropriate to talk about it now. So let f of x be a function whose graph is known, and let k be a fixed real number. The graph of the function g of x is equal to f of x plus k is the same shape of the graph of f, but shifted k units up if k is bigger than 0, and k units down if k is less than 0. So what this is saying is that if I add or subtract something to the outside of a function, then I shift the graph up or shift it down. So let's take a look at a couple of examples. Here is f of x equals 1 over x plus 3. So I'm adding 3 to the outside, so I'm going to shift up. But let's first look at the parent function so we know what the graph looks like. So here's the parent function, f of x equals 1 over x, and you can see that it's got two curves, one in the third quadrant and one in the first quadrant, and they're opposing each other, and our graph is going to shift this up. So let's go back to our graph. So again, I'm going to graph the parent function in red, and again this is a hard one to estimate, so it's just going to look roughly like it should. Okay, so we're adding 3 units to the outside, so that means we're shifting up 3. So we're going to use this asymptote to move 3 units up. So I'm going to shift this up 3 like that. And so that's going to give us our horizontal asymptote it's going to move from 0 up to 3, but our vertical asymptote is going to stay the same. So the graph of our function would look kind of like this. Okay, the next one is subtracting 3. And instead of switching back and forth, I'm going to go ahead and just show you what the parent function looks like. It's kind of like a cubic but laying on its side like this. And this one's subtracting 2, so we're going to go down 2. So this critical point here is going to shift down to here. And again, my graph is not a great drawing, but you kind of get the idea. And again, you're not going to have to draw these. The software is going to do it for you. Alright, so this one's got a combination. It's got both a horizontal and vertical shift. So let's put the parent function of the square root function. Looks kind of like this. So we're going to shift this 4 units to the left and 1 unit up. So we'll use this critical point. We're going to go 4 units to the left and then 1 unit up. So it's going to move to here and has the same general shape. All right, so next we need to talk about reflections. So we have two types of reflections. We have reflections about the x-axis and reflections about the y-axis. So a reflection about the x-axis flips the graph over the x-axis. And this occurs when we have a negative leading coefficient, or you can think of it as the whole function is negative. So g of x is equal to negative f of x. The other reflection is about the y-axis, and this happens whenever we make the x, we change the sign inside the function, so it's g of x is equal to f of negative x. So we're basically changing the sign of everything inside the function. This one occurs a little bit less often because of symmetry and even and odd functions. So you can only see a y-axis reflection if the function is odd. Okay, so the best example is to use for an x-axis reflection is to use f of x equals x squared. So the parent function is a parabola pointing upward with a vertex at 0, 0. Looks roughly like this. But our function, because of the negative, is a x-axis reflection. Looks kind of like that. And you'll see that every point reflects over that x-axis. Okay, so this is a good example for a y-axis reflection because it is an odd function. And again, we graphed the square root function earlier, so here it is again. And again, my graphs are not perfect. So a y-axis reflection would do this. And I've kind of got my graph a little distorted. This point should actually be down here, but we're not going to worry about that. All right, the next transformation is stretching and compressing, and this is all dealing with the leading coefficient and the value of that number that's in front. So the graph of g of x equals a times f of x is a vertical stretch if a is greater than 1, and if a is between 0 and 1, it is a vertical compression. So in other words, if a is like a 3, that's going to stretch by a factor of 3. So all the y values are going to be multiplied by 3. If a is between 0 and 1, like let's say 1/2, this is considered a compression because you're dividing every y value by 2 or multiplying by 1/2. So this function is the square root function being divided by 10, or you could say that it's 1/10 of the square root of x. So since this is between 0 and 1, we are compressing. So let's draw the parent function. I'm going to try to get this one a little bit more accurate this time. Okay, so since we are compressing, we are dividing by 10. So this thing's going to really flatten out. But it still has the same general shape, it's just a lot flatter because it's being compressed on that y-axis. So every value is divided by 10. Okay, so this is 5 times the absolute value. So recall from earlier that the absolute value function was that v. So it looked like this. and now I'm multiplying by a factor of 5. So our vertex stays where it is, but each y value gets multiplied by 5. So this point right here is going to go all the way up to here. So it gives the impression that it's narrowing. And my line curved a little bit, but it's straight. All right, so the last transformation is horizontal stretching and compressing. We really don't do that in this class, but you can definitely look at the theorem, and it's kind of the same thing, but it's the multiple is inside the function. And it's kind of opposite. It stretches if it's between 0 and 1. So in other words, that fraction, and it compresses if it's greater than 1 inside the function. But I'm not going to show examples of that for this class. Instead, I would like to go in and show you one example of the homework so that you can see how it works. All right, so I just popped into the software to give you an example of how to do your homework. So you see that I have a function r of x equals x plus 7 to the third power. So the first question is, what's the parent function? Determine the more basic function that has been shifted or reflected or stretched. So your first answer is going to be that parent function. And I've posted those parent functions in Canvas so that you can print that out and know what each parent function looks like and what it is. So this, because of my cubed, I know that my parent function is going to be x cubed. Okay, and next you're going to find the appropriate graph for x cubed. So again, looking at that parent function handout, you would see that this is the appropriate parent function. You would select that. Okay, and next it wants you to walk through the transformations. Now this one didn't have a whole lot of transformations in it. It's just subtracting 3 on the inside. So as we learned in the lesson, subtracting 3 means a horizontal shift to the right. So you would click the radio button and then you tell it 3 units to the right. See how the graph moved automatically? And then if it had any other transformations, you would go through and do the same process, but this one did not have any. So there's no reflections and no vertical shift as well. And then it wants you to tell, in the last step, it wants you to tell the domain and range. And you can bring up the graph from the last answer. And they kind of put it in the way. But your answer is this darker line. And you can see by the arrows that the domain is all real numbers. And this is a function that has no restrictions. So it's going to be all real numbers for the domain, all real numbers for the range. And then we're talking about this darker blue line. So there's a couple of ways that you can write this. You can use interval notation and say negative infinity to infinity, or you can pop into your keypad and just use that superscript R. And that's how the homework works.